Okay, let's start with phrase mining. First question first, why do we want to do phrase mining? Let's use the news articles, US news articles on April 9th, 2017 as an example. If we don't have any phrase mining, what we can do, the most straightforward way to analyze this document will be just plot a word cloud. It's basically based on the frequency of these words. And we have the visualization here. You will realize, okay, there's a word united at the top left corner, and there's a big unknown word DAO, DAO here. So you may have the question, which United is this United? Is the United States or UPS, the package delivery service? Or what's DAO? It's a person or a place or some miscellaneous entity we just don't know. This actually confuses people a lot when there's no phrase mining at all. Now, after the phrase mining, we do the same thing to the word cloud, but we are replacing the words by phrases. So we have this phrase cloud. So from here, you can easily understand, okay, wow, this is United Airlines and this is David Dow. This is an organization and this is a person. And all these news articles totally make sense because they are all talking about the well-known United Express flight incident happened in Chicago, Ohio airport, where a passenger, David Dow, was punched by the security guard and finally pulled out from the airplane. So from this example, we can see that phrase mining is actually a keystone towards understanding the text because phrase is actually a superset of the entities and the relations. And if we can upgrade all the word level things to the phrase level, it can immediately boost our understanding of this text data. We can use these phrases to do document analysis. We can use phrases serving as the anchors to index the documents in the search engine. We can even use the key phrase for document modeling, summarization, and many other things. Basically, whatever you are using the unigram, we can now replacing that by phrases. Let's formally define the phrase mining problem here. So we are looking for a ranked list of phrases with decreasing quality from a large collection of documents. The documents could be from different domains. For example, when the input are scientific papers, then we can expect that we can extract some high quality phrases related to the terminologies like data mining, machine learning, support vector machine. When the input are many news articles, then we can expect that we can extract some person's name, organization name, some many other like location, events, these kind of things. So there are many existing NLP-based methods like non-phrase chunking, parsing. They can give you some phrase lists, but most of them rely on extensive annotations from domain experts. Once you train a model for the news article, you cannot apply that directly to the scientific papers. You will need some additional human annotation to fine-tune or retrain your model to make it work for a new domain. So this is not something we want. We want a more automatic way. So there's a pioneer, unsupervised pioneer work, TopMine here. Basically, it's using the statistical signals, the significance score alpha. As you may know, alpha measures how many standard deviation away from the mean. So TopMine uses a greedy merge algorithm to segment sentences. For example, we have a title from the DBLP corpus, Markov blanket feature selection for support vector machine. If we're looking at every two adjacent tokens in this sentence, and we can compute their alpha scores. If alpha is more than a threshold, then we will merge them as a potential phrase. We will repeat this process until there's no such pair. So in the end, we will know Markov blanket is one phrase. Feature selection is a second phrase. 4 is a unigram, and support vector machine is the third phrase. However, there are some many other statistical signals that might be useful, such as point-wise mutual information and the chi-square. It's very difficult to unify multiple statistical signals in an unsupervised framework. So it's hard for the top mine to further extend to other statistical signals. So what we need here is some supervision. So we propose this SegPhrase later on to unify different statistical signals together using a classifier based on expert provided labels. This classifier will give a score between 0 and 1 to each phrase. 1 means it's a high quality phrase, while 0 means it's a low quality phrase. So the given label here will be binary. For example, if the input is about CS papers, we will say this paper is a low quality phrase because it's a stopword-like one. It's everywhere in every paper. It don't have specific meanings. And we will say support vector machine is a high quality phrase because it's the name of a popular classification method. You may wonder why this method is called SegPhrase. It's because we are using a phrasal segmentation here as well. Let me explain the details. The segmentation process in SegPhrase is slightly different from the top mine. It's not a greedy algorithm. It actually follows a generative process. We use the Viterbi algorithm to decide the optimal segmentation results, given the quality score estimated by the classifier. Remember that we are using statistical signals as features in the classifier. Most of them rely on the frequency. At the very beginning, we actually rely on this raw frequency. Basically, if we read the sentence raw Markov blanket feature selection for support vector machine, we will increase the counter for Markov by 1, Markov blanket by 1, Markov blanket feature by 1. Basically, every n-gram, we will increase the counter by 1. Then what if we have the phrasal segmentation results? We can now compute the rectified frequency by only counting the phrases as a whole unit. If you look at this example, if we have such segmentation results, we will only increase the frequency of Markov blanket by 1. We will never touch the counter of Markov or blanket by looking at this sentence. As a result, we actually have more accurate statistical signals using this rectified frequency. Then why not? We can build a better classifier. So the key idea of the SegPhrase is we build a mutual enhancement loop between the quality estimation and the phrasal segmentation. We use the weak supervision to train the classifier which unifies multiple statistical signals. This classifier is further used in the phrasal segmentation, which can further rectify the phrase frequency. So using this rectified frequency, we have better statistical signals, then it forms a mutual enhancement loop. So as I mentioned before, this SegPhrase still requires expert-provided labels. Then the question becomes, how many labels do we need? Actually, not that much. For about 1 gigabyte raw text, we only need 300 well-designed binary labels. You may think that labeling 300 phrases is not a big deal, but the key here is how can we know which 300 phrases should we label, given millions of candidate phrases? This actually requires a lot of domain-specific knowledge, and you must be familiar with the SegPhrase model and features. This is a big problem deviating from our automatic principle. When we are building the SegPhrase model, we actually did something similar to the active learning. We initially annotated 10 labels and run the model and manually inspect the results and try to figure out, okay, where are some possible improvement we can make by including more labels. And we are very familiar with the statistical signals we have. So it's fairly easy for us to do this runs by runs. We finally reached 300 labels. So it could be very time consuming, and the annotator will need strong domain-specific knowledge. As a result, we further developed AutoPhrase to replace the expert-provided labels by a public knowledge base. How can we do that? In knowledge bases, there are many high-quality phrases freely available. Where are they? For example, in Wikipedia, if you look at those pages, those page titles are mostly high-quality phrases. And there are also some internal links within the Wikipedia. If you look at the anchor terms they have for those hyperlinks, they are high-coded phrases as well. So by leveraging these phrases, we can get a large set of high-coded phrases there. And from the input raw corpus, we can also generate the candidate phrases by using the frequent n-gram mining. By taking an intersection of these two sets, we now have a free, clean pool of high-quality phrases. You may have a question like whether the knowledge base can actually cover most of these high-quality phrases. The answer is no. The knowledge base are usually incomplete. There are way more phrases to be discovered from this candidate pool. So then the key problem here is there's no mention of the low-coded phrases at all in the knowledge base. So how can we build a classifier with only positive samples? So we come up with this idea. So we do some negative sampling from the noisy negative pool to make this possible. If we think about that, we are using the frequent n-gram as a candidate phrases. The ratio of the numbers of high-quality phrases to be discovered over the number of remaining candidate phrases should not be very high. You may ask why. So let me give you an example. I have a favorite terminology which has 6 words there. It's called NP hard in a strong sense. This is a long high-quality phrases and it has 6 words. All its subphrases are at least as frequent as itself, and therefore they must be there in the candidate phrase pool. But in fact, most of them are not high-quality phrases. So we did some human estimation based on some sampling, and we realized, okay, this ratio is only about 10%. So this gives us some idea about this noisy negative pool. We have a lot of candidates here. Only a small portion of them are possibly high-quality phrases that we want to discover. So in this way, we can conduct some negative sampling. It's feasible because the ratio here is really low, just 10%. The key ideas of the AutoPhrase are using distance supervision to replace the expert-provided labels and use the ensemble learning and negative sampling to build a robust classifier. So more specifically, we will first build a single classifier based on random sample of positive and negative labels. The classifier mainly has the errors caused by the noisy negative labels. From our empirical evaluation, the error rate is also about 10%. Then we are going to do some ensemble here. We are going to combine n independent classifiers together, and we simply average their prediction to do the denoise. If we think about that, if they are really independent to each other, the majority of the classes, if the majority of the classifiers makes the same error, then it will make the error. Otherwise, it will be correct. So theoretically, this error drops exponentially when we have more and more classifiers. So ideally, if we have 1,000 of such independent classifiers, we will eventually have a very low error rate. So that's the idea. In the reality, there might be more noise during the model training. So we need to do some evaluation to check whether our idea works well in the real world data set. So our evaluation looks like this. As our output is a rank list of the phrases with decreasing quality. So we are going to do some annotation from a human expert for these phrases by saying 1 for high quality phrases and 0 for low quality phrases. For example, NP hard in a strong sense will be annotated as 1, and NP hard in a strong will be annotated as 0. During this evaluation process, the experts are encouraged to use search engine like Google to better understand those phrases because if they are not very familiar with. During the annotation process, the experts are encouraged to use a search engine like Google to better understand those phrases they are not very familiar with. Based on the expert evaluation results, we compute the precision and recall at every rank. And then we can draw the curve of the precision and recall. In an ideal ranking results, the precision recall curve should look like this. In an ideal ranking result, the precision recall curve should look like this. It's kind of a rectangle. As we mentioned before, that our methods are designed to be effective in multiple domains and languages. We first evaluate the results in 3 domains: CS papers, Yelp reviews, and Wikipedia articles. We mainly compare AutoPhrase with SegPhrase and Stanford NLP parser. SegPhrase has outperformed many unsupervised methods like TopMine, so we didn't include the results here to make this figure cleaner. The Stanford NLP parser can extract noun phrases and the verb phrases as well from the sentences. We use a popular TF-IDF and text rank to rank the extracted phrases. TF-IDF is a popular measurement in the information retrieval. TF is a term frequency and IDF is the inverse document frequency. Text rank is similar to the page rank. We simply construct a graph of phrases and build edges as their co-occurrence within the given sliding window. Then we run a random walk on this graph and compute the page rank. As you can see here, AutoPhrase have always the best performance. We further conducted the experiments in different languages. Since SegPhrase is originally designed for English, we introduced its variant wrap SegPhrase here. Basically, we encode the non-English tokens using English letters. The first token is marked as A, second token will be B, third token will be C, and the 27th token will be AA, something like that. And I also would like to highlight here on the Chinese data set here, we compare with the popular supervised Chinese phrase mining methods, JBA segmentation and ANSJ segmentation. They're using conditional random fields and a hidden Markov model trained on annotated Corpora. As you can see here, AutoPhrase always performs the best. And there's a huge gap between the AutoPhrase versus the SegPhrase, especially on non-English corpus. And also, we can outperform the supervised Chinese segmentation model, which is really encouraging. After the quantitative evaluation, I'd like to show you some example results. The Chinese dataset is one of the most challenging datasets. And so, as you may know, the tokenization in Chinese is also very difficult because there's no white space. Meanwhile, the volume of the Chinese Wikipedia is much smaller than English and Spanish wikis. This makes the distance supervision hard because the possible high-quality phrases we can get from the wiki is more limited. So let's look at the Chinese phrase results. The first column is the rank, the second column is the phrase, and the third column is the translation. The underscores here are inserted by our tokenizer. While some of the tokenization results might not be accurate, but AutoPhrase can always find high-quality phrases. For example, if you look at this, even around 100K rankings, we can still find meaningful phrases like this. And in fact, most of the high-quality phrases are not covered by the Wikipedia's positive pool. So here in the positive pool we got, we only have the 29K phrases in total. But AutoPhrase actually finds more than 100K high-quality phrases with a quality score greater than 0.5. So it confirms that there are way more high-quality phrases that we should find from the candidate pool. So far, we have discussed a series of our phrase mining methods. We have open source codes and they have been adopted in many companies and organizations, especially for AutoPhrase. For example, US Army Research Lab, ARL, is using them to analyze their battlefield reports and gain insights from the results. Facebook is using AutoPhrase to their posts and articles, try to upgrade their textual signals from the word level to the phrase level, and therefore improving and therefore improve the user experience. Yelp and TripAdvisor, they're using our AutoPhrase to analyze their review corpus and try to derive more interesting clusters like this. If you group these hotels in this way, we can form a catcher show collection and near the highline collection. So it will be more interesting for the users to explore the neighborhood. Last but not least, our method has been applied by the IMF, International Monetary Fund. They're using our AutoPhrase to analyze the news article and analytic reports and try to find some signals related to the stock market. So all these phrase mining methods has been consolidated together in this book, Phrase Mining from Massive Text and its Application. So I hope you have enjoyed the phrase mining, and now we are going to move to the name entity recognition. Let's talk about the name entity recognition in neural language models. The first question you may have is, what is name entity recognition? It is usually, we usually use NER for abbreviation. It's a subtask of information extraction, and there are two major problems, like where are the entities and what types are these entities. And a name entity is typically a real-world object. Let me give you an example. Suppose we have some sentence like Jim bought 300 shares of a company in 2006. So we want to annotate Jim is a person, that ACME Corporation is an organization, and 2006 is a time. So in the supervised method, we want to curate the data in following a sequence labeling framework. There are two popular labeling schemes. One is BIO, another is BIOES. B here is the beginning of the entity, I is inside the entity, O is outside. E means the end of the entity, and S is a singleton entity. And based on some experiments, we have learned that BIOES is slightly better than BIO in practice. So if we have the same example sentence, we are going to annotate every token following this scheme. So suppose we're using BIOES here. Jim will be annotated as S person because this is a singleton entity, and ACME Corporation will be marked as B organization and E organization accordingly because this is the beginning and the end of the entity. So the other tokens non-entity tokens will be marked as O. There are two pioneer neural models, there are two pioneer neural models, LSTM-CIF and LSTM-CNN-CIF. These two models are first a few neural models that outperforms the model based on handcraft features. So basically, the major difference between the LSTM-CIF and LSTM-CNN-CIF is about their character level representation learning. In the LSTM-CIF, it's using bidirectional LSTM for both word level and character level, while the LSTM-CNN-CIF model uses convolutional neural network for the character level. Similar to our automatic philosophy, we have a data-driven philosophy for this NER topic here. The key here is we want to enhance the NER performance without introducing any additional human annotations. There are a few key questions we can explore, and in this tutorial, we are focused on the first two. Can we use the massive amount of raw text to help, or can we use the existing domain-specific dictionary to help? Let's first look at the massive raw text. As we all know that word embedding has changed the text mining or NLP research from 2013, and more recently we have the language models, which is kind of the new tools, new weapons that we can use to attack NLP problems. So using the language model, we can have some better representation at the word level and character level, and we can also combine these language models at different levels for a better performance. As you can see here in this list, we have many papers in recent years. They are also achieving the best paper awards in different conferences. So let me first briefly introduce what is the language model here. Let me first briefly introduce what is a neural language model. A language model here, language model basically describes the generation process of the text. We are going to make prediction for the next words based on the previous context. It's very natural for the human language. Like after I say a few words, you may have some expectation about what's the next word to make this sentence fluent. So in the neural language model, we are not only looking at the tokens, we transfer the token here into the word embedding and then pass it through some LSTM or recurrent neural network units to understand the semantics or context. And eventually we have the hidden states for everyone. And after another linear layer, we will be able to make prediction. It's basically a softmax function to make prediction over the entire vocabulary. So the major advantage of this language model idea here is it doesn't require any human annotation. It has nearly unlimited training data. As long as you have raw corpus, we can use that to train the neural language model. So it's possible to train a very large neural language model just because we can have almost infinite number of raw text as we are writing and posting every day. So another advantage that after the experiments, we realized the resulting model can really generate sentences of an unexpectedly high quality. So let me give you some example. So we can train, let me give you a few examples. One can train a character level language model based on all the markdown files we have from GitHub README files. So as you can see here, this snippet is actually generated by a character level language model. Believe it or not, it has the valid syntax. There's a very interesting Twitter account, Deep Donald Trump, this Deep Trumps. It tried to mimic the President Trump to make some posts. It's trained on the Trump's transcripts and then try to generate a few interesting sentences and make a few posts every day. So it actually fooled many Twitter users at the very beginning. As you can see here, it has 26,000 followers. It makes some sense by looking at this sentence. It has some Trump flavor here. So let's go back to the NER. How can we use the language model to improve the NER performance? The first idea here will be co-training. We propose to use the character level language model as a co-training objective. So why we want to use a character level? Because the NER training set is typically small, and the character language model has less amount of parameters to train. So, and it's more efficient and it's robust to the pre-processing. So we can just train the character level language model based on the same training set of the NER. We don't require any additional annotation, and we don't require any additional corpus. So we just have the same training set and we can improve the performance. But later, as some of you may know, that people realize like the pre-training of the language model is very powerful, but you will need a lot of computational resources to finish the pre-training on the huge amount of raw text. In this ML idea, we will pre-train the language model and fix the parameters of this language model and just concatenate the two directions hidden state together, forming the contextualized representation here, and combined together with the character representation and the word embedding, and then feed it to the traditional LSTM CIF layers. So this is kind of the Elmo idea. It has been applied to other NLP tasks like question answering and stance detection as well. Elmo can improve the performance of the NER, but it will be relatively slow in the inference stage if you want to use a large neural language model. So in this LadyNet, we propose to do some pruning to the language model. Instead of using a wide and shallow neural network, we designed some layer-wise dropout idea and a dense connection to make sure the model is prepared for the pruning. After the pruning, we will have a fairly small model tailored to the end task. So eventually the inference could be very efficient. If you look at this table, you can see that Elmo requires a lot of number of flops, while the LadyNet is much smaller compared to the Elmo ones. And our finally pruned version is really small. We only need 6 million number of flops to achieve a similar or sometimes even better performance for the same NER task. The current state-of-the-art model for the NER, supervised NER, is this player. It's not only using the pre-trained language model at the character level or the word level, it's using the pre-trained language model at both level. So it's basically similar. It's very similar to what we have in the LM, LSTM, CIF, but the difference here is it's doing the pre-training on additional training corpus. Then it achieves the best performance among all these compared models. Google proposed a BERT to use a transformer instead of the LSTM or RNN modules, and then they can enable the mask language model and the next sentence prediction. And you can also conduct fine-tuning after the pre-training on each task, so you can tailor BERT to different tasks. So here, BERT is also tailored for the NER model and achieves a fairly good performance. As summarized in this table, we can see that incorporating language model of different levels can help us to achieve better performance here. And you can see among all this performance, Flare is arguably the best. The second question will be, can we use a dictionary instead of the human annotation to build the NER model? So this becomes a distantly supervised NER setting. The input will be the unlabeled raw text only, and we have an entity dictionary coming along with this raw corpus. This dictionary basically has 3 columns. The first column will be the entity type. The second column will be the canonical entity name. The third column will be a few known entity synonyms to this entity. Eventually, we want to train an NER model that can recognize entities of the entity types appeared in this dictionary. Note that we want to recognize entities goes beyond the dictionary itself. There are some existing methods on this distantly supervised NER. The most straightforward idea here will be just do some string match or rule-based things to recognize entities. But in this way, you can never recognize those unknown entities. The second thread will be auto, entity, SwellShark, and class type. They all leave the entity span detection to experts. Remember that in NER, there are 2 tasks. Where are the entities and what types are these entities? So they leave the first task to the human expert and only build a model for the type recognition. All these methods will ask the human expert to design some POS tag-based rules, maybe some regular expression to recognize all these entity spans. So they will only work on the second problem about the entity types. And the last type of the method is AutoNER. This is a method we propose to attack these NER problems as a whole, including where are the entities and what types are these entities. So let me introduce a little bit about the baseline SwellShark. This is a distantly supervised typing method. It uses the data programming techniques for entity typing. But what you need to know here is it requires a human expert effort in the first step for this candidate generator. They are mostly regular expressions based on part-of-speech text. So in our AutoNER setting, we propose to resolve this distantly supervised NER problem by using 2 dictionaries. The first dictionary is a core dictionary, which leads to high precision but low recall matches. So we're still using the string match to generate the distance supervision, but we will later use such supervision to train the models, to train the NER models. The high precision here means we expect that the precision could be as high as 90%, while the low recall still covers around 50% of these entities. A full dictionary here is designed to get a high recall but low precision recall. So remember that in this full dictionary, we actually don't know the entity types because we introduced the out of dictionary high quality phrases as new entities. We're using the AutoPhrase here to adding complementary phrases as this into this full dictionary. The the newly introduced phrases, because we don't know their type, we just say they are unknown types. For those unknown types, there could be any BIOES plus any type because they could be anything. They could be some verb phrase. They could be some entities that we are not interested in. They can be the entities we're interested in. So it can be anything. So just give you an example. If we look at this sentence, we have the high quality phrases matching these two tokens. We don't know their types, so they could be anything. So in the traditional CRF layer, there's only one feasible path for this decoding, but now we have multiple ones. So we propose this fuzzy LSTM CRF model as a new baseline we can compare with. So it has a summation here in this numerator to address this multiple path issue. And during the inference, it still gives you the best explanation using the Viterbi decoding. So in this way, we can still have the final output for the NER. But if you think about that, if whether this is the best solution we deal with these unknown tokens, maybe it's not. So we propose something different here. Instead of labeling each token, we propose this novel tie or break labeling scheme to handle those unknown tokens. So basically, for every two adjacent tokens, the connection between them is labeled. If these two tokens are matched to the same entity, it's a tie here. If any of them is unknown, it's just unknown. Otherwise, it's a break. So let me give you an example here. So this is a sentence from Amazon review for a laptop. So you can see this ceramic unibody is a matched entity in the dictionary, so we mark a tie here. And then we have an 8 GB RAM, which is a high quality phrase we found from the AutoPhrase. So we will mark everything unknown if it's adjacent to this phrase. If there's another token after the RAM, there will be another unknown. So for other connections, they are all break. And then every two adjacent breaks, they form a possible entity span. If we actually match these words from the dictionary, we will know its entity type. Otherwise, we will say it's non-entity, it's not an entity at all. So it's quite safe because for the phrases here, we will have one more token before and after that to forming the entity span. So it's reasonable to say it's not an entity. During the training here, we will not calculate the loss function at the unknown places. We will train a binary classifier for this tile break, and we will also train a k+1 classifier for the types. K here is the number of types we have in the dictionary, and the +1 is designed for this non-entity type. During the inference, we will first run the binary classifier to find all these breaks, and then for the adjacent breaks, we will send this span to the k+1 classifier, and then we get the entity types. So in this way, we will get the NER prediction as the same as the other NER models using BIOES labeling scheme. Okay, so let's do some comparison of this NER model on the biomedical domain. We have conducted the comparison on the BC5 CDR dataset and NCBI disease dataset. We listed the supervised benchmark using the gold annotation from the human experts as a reference here, which is kind of the upper bound or the goal we want to achieve. The SwellShark is the baseline from the Stanford we mentioned before. It requires certain human effort to design a regular expression or tune the special cases. Dictionary match is a way we generate our supervision from the core dictionary. Fuzzy LSTM CRF is a method that we propose to address the unknown tokens as a baseline, and AutoNER is our method. As you can see here, AutoNER achieves a very competitive performance. It's the best among all these methods without any additional human effort other than the dictionary. It's also very close to the supervised methods performance on the BC5 CDR dataset. And it's even outperformed the SwellShark on this dataset. So you can see there's a high potential that we can use the high quality dictionary to initiate the effort of NER. We can build a model first, and then only ask the human expert to correct those a few mistakes there to get the gold annotations. In this way, we can build the NER model with less amount of human effort. So in summary, using neural language model, we can leverage the massive amount of raw text to help. Using the high quality dictionary, we can build a reasonably good NER model. So in the third part of the chapter 1, we are going to briefly discuss about the relation extraction and attribute discovery, mainly from the meta pattern perspective. So meta pattern is a pattern at a meta level. So we are going to replace some entities by their types. For example, we will replace the Donald Trump, these two words, by $person, because we can recognize this is a person. So we can have some patterns like $person, brackets, age, dollar digits. So we can use this pattern to recognize the attribute age, and also we can fill the value of this age by matching these digits. So we can use this meta pattern to discover those attributes. We can extract the relationship between two entities, and we can further use that to refine the name entity recognitions, entity boundary, and type maybe in future. So that's something interesting for the meta pattern mining. There are some previous work on finding EAV, which is entity, attribute, and value patterns or typed patterns. For example, for those OpenIE work here, they are focusing on those the lexicon level patterns with these specific instances there. Google's Wikipedia work has tried to make these patterns at the abstract level using this attribute entity or value to replace those specific instances, but they are too abstracted to some extent. Therefore, we propose this meta pattern here, try to find some right granularity for these different entities, and then try to distill the patterns at the meta level. The attribute discovery task actually has two folds. The first one is we want to find all these instances. We want to know what's the age of this specific person. We want to know what's the specific relationship between these two entities. There's another fold is that we want to understand all this type level relationship. We want to know that, okay, person may have an attribute age, and the country may have an attribute of the president, and two person may have some relationship like friends. So we want to understand both this instant level and the type level things in the same framework. So in this meta pattern methodology, we propose to do this meta pattern together with these instance things. So there's no heavy annotation required, there's no domain knowledge required, there's no query log required. What we need here is only the raw corpus and the some existing knowledge base or dictionary for us to generate some distance supervision. So we are going to do some meta pattern segmentation at the type level. It's very similar to what we have done in the AutoPhrase. It's similar to the Phrasal segmentation, but it's just on the type level. So after we do some segmentation, we will be able to recognize those kind of high quality phrases here, but they are now the meta pattern. And after that, we're going to generate more instances based on this pattern match. And this can be further used to adjust the frequency of these kind of patterns. It's very similar to the AutoPhrase, it's just at the type level. So before we do the meta pattern mining, we need to figure out where are the phrases and where are the entities, where are the possible types of the entities along all different granularity. So these are a few pre-processing steps we need to do. And in the meta pattern quality assessment and the segmentation, slightly different from the phrase mining, we have something new here. We need to think of the completeness and the informativeness based on the granularity. We want to vary different granularity and see which one is the best. We want to group the synonymous patterns together by applying some clustering, and then we can combine all these things together, consolidating these instance level things, say we are more confident about this instance because there are multiple patterns indicating this is the right relationship or right attribute to these entities. And it's also interesting that we want to adjust the types in the meta pattern for the appropriate granularity. We want to make sure that age is the attribute for a person. It's not a specific attribute to artist or the politician. It's quite a general attribute to person. So we will look at the distribution of these things and we realize, okay, person actually dominates this. So we will stop the pattern at the person, this type level. And if you look at the president, we will realize, okay, location only have a very small portion of this president, while we actually have the majority of them by country or by the country. That's why we will assign the president as an attribute to country instead of a location. We will assign it to politician instead of a general person. This is another novelty of this meta pattern. So here are some examples we can recognize from this row corpus. It's very nice and clean. We can find patterns for president, for countries, and we can find CEOs for those companies. Yeah, so you may look at these results and you can see, okay, it's actually very accurate. Here are some other examples related in the scientific domain. Looking at the medical science corpus, we can find some treatment for the diseases. We can also find some resistant relationship between bacteria and antibiotics. There are some further enhancements of the MetaPad. We won't elaborate them in details, but if you feel interested, you can read both this TruePy and the WWPy. They are mainly working on how can we find the reliable patterns and improve the quality of the instance we can extract, and also how can we leverage the parsing structure to mine those long distance relationships which are not adjacent to each other in sentences. One follow-up work of this meta pattern has been applied to the biomedical domain, mainly focusing on the nested name entity recognition. Nested entities are very popular in the biomedical domain because most of these terminologies are created by humans following some rules. For example, this one chemical plus some suffix, then it becomes a protein. So this could be something very interesting in the biomedical domain. And nested entities are very important. Based on some statistics, we know that about 17% of the entities in a certain data set are embedded with another entity. And nested entities are very useful in many downstream tasks. This is a very crucial problem in the biomedical domain. The goal of this work is try to conduct this nested bioentity recognition using very limited amount of supervision. So the key idea here is nested structure is usually a pattern level phenomenon. For example, as I mentioned before, chemical plus some suffix, it becomes a protein. Gene mRNA release becomes a process. So we want to design a framework that we can start with the flat, the innermost name entities, and then try to do some unsupervised meta pattern extraction. And then we use a few shot learning idea to generalize this nested name entity from these meta patterns. And we do the evaluation on the nested NER benchmark data set in the biomedical domain. We also compare our method with this Pub Tator, which is a very popular tool in the biomedical domain, but it requires extensive of human annotations. So here's the overview of our framework. We start from the input corpus without any annotations. We will run some flat NER model. We can recognize some innermost. We will run some traditional name entity recognition model. It will only recognize the innermost entities, which is kind of the minimum semantic unit. And then at this meta level, we are going to discover the meta pattern and try to use this meta pattern to further generate more similar patterns using some pattern expansion here. And in the end, we can leverage all these patterns to detect those more complicated nested entities. So in this way, we will combine the flat entities and nested entities together in the end. in this work, we mainly borrow the set expansion idea we published before and adapt that for the meta patterns. So it's basically a pattern-based method, try to figure out what are the common contexts of those seed patterns, and then try to figure out whether we can find some similar patterns. So if you're interested, you can read this set expand paper and also this pattern enhanced NER paper for the details. So set expansion essentially combines the frequency and the context similarity. But unlike entities, some meta patterns, they may be extremely frequent. For example, chemical. Chemical is everywhere in those biomedical publications. We utilize some further information about these sets. Remember that we are trying to recognize different entity types. So these entities should be mutually exclusive to each other. So we leverage this as some additional constraint to the set expansion to make this process more accurate. So here are some results we can find. The first one is based on their embedding similarity. The second one is the raw results from the set expansion. And the last one will be our pattern enhanced name entity recognition, which included the exclusiveness of different sets. So we marked the correct patterns using the black, while we colored the wrong patterns using gray. So you can see that our method eventually performs much better than the previous work. We also do some systematic evaluation. We also use NDCG for the ranking performance, and we use a recall. We use a number of correct instances to evaluate recall. And from these results, you can see that our pattern enhanced name entity recognition method can outperform all the baselines. So here are some case studies that our method can actually use only 2 seeds and detect a lot of biological process and treatment entities. And it's also, and if we have fine-grained flat NER detection, then it can further improve our performance. We also compared our results with Pub Tator, and you will find that there are a few cases that our method performs much better than the Pub Tator. If you look at this, Pub Tator will favor those short and flat entities, while our method can not only give you those correct flat entities, but we will also recognize those long nested entities, which are very important for the downstream application. Okay, that's all for my part in chapter 1. I will hand it over to Dr. Meng Jiang.